Hello, everyone. Hope you're doing well. Hope you're hanging in there. Not too much more to go. First thing I need to do in the unit of logarithms, if we were in class, you would have a cheat sheet. I'm going to leave this cheat sheet up. You should probably copy your own. But what we need to do is be good at powers. So, for example, if I put a 2 here, you have to know that 2 to the power of 2 is 4, and 2 to the power of 3 is 8, and 2 to the power of 4 is 16, 2 to the power of 5 is 32, 64, 128, and 8 is 256. I don't think we have to go much higher than that. We need the family of 3s. You need to know that 3 squared is 9, 3 to the third is 27, 3 to the fourth is 81, and 3 to the fifth is 243, and that's probably as high as we need to go in that family, maybe 729, but I doubt it. We don't need to do 4s because there's a 4 here. So anytime I get a 4, I can break it down to a 2. And we'll talk about this in a minute. If I go to 5s, 5 squared is 25, 125, 5 to the fourth, 625. And I don't think we need to go much higher than that. Family of 6s, 6 squared is 36. 6 to the third is 216, and that's just probably as high as I need to go with that. 7s is its own family. 7 squared is 49. 7 to the third is 343. 8. I don't need to go to 8s because there's an 8 here, and if there's an 8 here, then 8s can break down to 2s. So we'll talk about that. 9s, I don't need 9s because there's a 9 here. So if I have a 9, I can break it down to 3 squared. And then 10s would be your last if you don't know 100 and 1,000 and 10,000. So it is important to keep this. We're going to reference this in our next section. All right, everyone, we're going to be talking about real number exponents, and we just need to make a connection between bases and exponents. And why we're doing this is because when we get into logarithms, if you understand these connections, you'll be much stronger. So what they're trying to say is if the base here is equal to the base here, then your exponents will be equal. So for example, if I can't make 2 any smaller, but now I have a number 8. Now, if we referenced our index card we just made, here's the number 8. Well, how can I make that smaller? I can make the number 8 2 to the power of 3. So now I can say 2 to the power of 3 is a number 8. Well, now that these 2's are the same, I can then say x equals 3. And that's all we need to do. We need to get our bases to be the same so that then we can make the connection with the exponent. All right, our first example, let's check out our bases, 2 and 2. The bases are the same, so basically we're going to knock them out and say x plus 5 equals 5, and I'm going to subtract over and x equals 0. So that one's kind of silly, but if you see here, I want this side to be the same as this. So all I need x to be is 0, and then therefore both sides would be 2 to the power of 5. Our next problem, this is the base 2. This is not a 2. I never want to go bigger, so I don't want to make the 2 become a 4. So I'm going to leave the 2 here, and that's the smallest it can become because if we look back at our index card, 2 is the smallest family I have. So if I go to here, now how can I make a 4 become a 2? Well, hopefully you realize that 2 squared is 4, but now we need to remember there's still an x here. So now what happens, now that these are the same, I can pretend that they're not really there. So I'm going to take x plus 1 and set it equal to, now remember, this is an exponent raised to an exponent, so what do I do with them? I multiply. So now I have x plus 1 equals 2x. I'm going to subtract x. I get 1 equals 1x, and x is 1. So does it make sense? 1 plus 1 is 2 squared, the same as 4 to the power of 1. Yes. But the whole reason we're doing this is because when we get to logarithms, we need to be good at going to smaller bases. Okay. Let's look at this one in which 81 and 27 are totally different numbers. Neither of them are very small. So I'm going to go back to my index card. Here I see 81. Here I see 27. So the good part is both of them lie in the family of 3s. So now I'm just going to ask myself, how can I get this to a 3? Well, 3 to the power of 4. Okay, that's 81. What's 27 is 3 to the power of 3. So that's in here. And now I have 2x minus 3 and 7 minus x. Remember, they didn't go away. So what happens now? Now I can ignore the 3's because the bases are the same. And now I have 4 parenthesis 2x minus 3 and 3 parenthesis 7 minus x. Remember, we have to multiply them both. So 8x minus 12, 21 minus 3x. I'm going to add over, that's 11. I'm going to subtract 12, which is 9. And I'm going to divide by 11. And x is 9 11ths. So it's okay. It's not always going to be a nice number. Okay, just on track that I did everything right. 8x minus 12, 21 minus 3x. Perfect. Okay. Okay. So then we get 9 11ths. Okay. And now we have to come to this one. So go ahead and take a second and look at the problem. So I do have 32 and I have 1/4. Fractions are scary. So one thing we're going to do is we're going to get rid of this fraction right away. And this is very important because people will forget. Fractions scare me. I can get rid of a fraction because remember in the last unit, 4 to the negative 1 was 1/4. So anytime I have a fraction, I can rewrite it, but now I'm going to use a negative exponent. Now, I'm not done. All I did was change that 1/4 to a 4, bringing it to the power of negative 1. Remember, these are powers. They're up high, they're powers. So now I have 32 and 4. So if I go to my index card, here's 32, here's 4. Both of them are in the family of 2's. So 2 squared is 4, 2 to the 5th is 32. So now I'm going to write 2 to the 5th, but there's a 4x here. 4 is 2 squared, but now it's 2 to the 2nd, but there's a negative 1. So you can't lose that. And then I have 5 minus 7x. Once we get this and this the same, they kind of cancel, and I get 20x, and I get negative 2 parenthesis 5 minus 7x. I get 20x. Everybody get where I got that? I multiplied. Negative 10, 14x. Negative times negative becomes positive. I'm going to subtract 14x. That's going to give me 6x equals negative 10. Divide, and x is negative 10/6 or negative 5/3. Okay? So you get a fraction. That's okay. Final answer. It's okay. So you could go back and plug them in and check if you wanted with a calculator. All right. The problem I'm doing is totally different. I'm just going to do it. Not that I have to test on it or do anything, but I just want to explain. In this problem, the base is completely missing. I have an exponent. What I want this to read is x equals some number. So in order for me, I have to figure out how to get rid of this. Well, in math, in order for this to become x to the 1, I need to multiply this by its reciprocal, because 2/3 times 3 over 2 is going to give me 6 over 6, which is 1. So if I do that, that will turn this to a 1. Well, what happens is if I raise this, I need to raise this side. So what occurs is now I need to, I'm just going to take that 1 out. So now I'm just going to rewrite this as x equals, and now it becomes 9 to the 3 over 2. Well, this is kind of what we have already done. 9 can become smaller. If I look at my index card, here's 9. What is 9? 3 squared. So I'm going to write it as 3 squared raised to the 3 over 2, which is okay because fractions here, this is going to be 2 times 3, which is 6, divided. Now, just be careful though, because this 3 is not going away in this problem. There's still a big 3. I'm multiplying these together. So 2 over 1 times 3 over 2 is 6 over 2, which is 3. So this becomes 3 to the 3rd, which is 27. So totally different problem than the other ones, but I just wanted you to see the difference. In this one, the variables are the exponents. In this one, your variable happens to be a base. So just be careful. They're types of problems, but we're going to practice our specific ones.